So welcome everyone to our seminar today. So our speaker today is Raphael Ponge from Sichuan University and the Sichuan province, 1,000 talents. So Raphael is going to tell us about analysis on curved non-commutative tori. So please, Raphael.
All right, so thanks Xiang and Guyan for giving me the opportunity to speak in the seminar. So I'll speak on analysis on curve noncommutative tori. So the main result concern construction of Laplace-Beltrami Operator, version of Gauss-Bonnet theorem. So I also speak about various laws, give some version of contrast theorem and Kahn's integration formula for noncommutative tori. So I also speak about briefly about scalar curvature, and if time permitted, maybe mention a local index formula. So the point is that all these results are established for arbitrary Riemannian metric. So these are Riemannian metric in the sense of Jonathan Rosenberg. And the motivation for this work is twofold. Okay, so first, I would like to extend analysis on conformally flat noncommutative tori by various other people, Kohn, Tretkov, Kohn, Moscovici, Fatizadeh, Al-Rali, and others. So they mostly focused on conformally flat noncommutative tori. And I would like to extend this analysis and the result to general curve noncommutative tori. And by curve noncommutative torus, I mean noncommutative torus equipped with an arbitrary Riemannian metric. So I will recall definition of Riemannian metric in a few slides. Another motivation is to, since you have a notion of Riemannian metric, and also have a notion of pseudo-differential calculus, which is goes back to Kohn. We like to extend to non-commutative tori various results on spectral geometry for ordinary Riemannian manifolds, such as, for instance, local various law, and as well as looking at the local index theory. So there's a first glimpse of a local index theory that I will give at the end of the talk. So let me recall definition of non-commutative torus. So consider n-dimensional non-commutative torus associated with a real antisymmetric n by n matrix, denoted by theta. So the entries of theta are denoted theta jk. And the non-commutative torus is a non-commutative space whose C-star algebra, C theta n, is generated by n unitaries, U1 through UN, satisfying this relation. Okay. So for theta, when theta equals 0, you recover the ordinary, the C-star algebra of continuous function on the ordinary torus. So I just like to stress out that that you have a dense basis of C theta n given by the monomial UM, where m is a multi-integer, okay, and UM is so given by this U1 M1 dot UN M. Okay, so you have a measure theory, so which arises from canonical trace, which is given by we such that tau of 1 is 1 and tau of UM is 0 when m is different from 0. So using tau can define inner product by this formula. So inner product of UV is tau of V star U. So in fact, what we do is construct the Hilbert space for the GNS representation associated with tau. And in particular, the action of C theta n on itself by left implication extend to a star representation. Star representation in L2 theta n. Okay. So there are also dynamics on C theta n, which leads to a smooth structure. So dynamic gives rise to a canonical derivation d1 so that should be defined as follows. So the convention is that dj uj is I uj, so I is the square root of -1, and dj uk is 0 when k is different from j. And the smooth non-primitive torus, so it corresponds, so this identical derivation define an action of Rn, and a smooth non-primitive torus correspond to elements that are smooth with respect to this action, and can be shown to be to agree with the element which is given by a Fourier series in terms of the unitary U, capital U M, and the coefficient of the Fourier series have a rapid decay, that is an S, script S of the M. So this is analogous to the description of the smooth function of the ordinary torus in terms of Fourier series with rapid decay. Okay, so the C infinity of theta n is some interesting topology. So it's a Frechet star algebra, and it is closed under holomorphic functional calculus. So in particular, closer under holomorphic functional closeness under holomorphic functional calculus is an important property for business. Okay, so how we define a Riemannian metric on non-primitive tori? So we start by defining a module of vector field. So it's noted script x theta. So defined as a left free module, it's generated by the canonical derivation d1 dn that defined the previous slide. So definition of due to Jonathan Rosenberg is that Riemannian metric is given by a positive invertible matrix G with entries Gij. So the entries Gij are the smooth elements are smooth, and they are self-adjoint. So this gives rise to a Hermitian metric on x theta by this formula, okay, because x theta is a basis given by the derivation d1 dot dn. Okay. And so what? And the self-adjoint condition here is actually, so it means that the coefficient of the Hermitian metric respect to the basis di are self-adjoint. Okay. So yes, so so this is analogous to the condition that requires that the Riemannian metric takes a real value on vector field. So in commutative case, having a real value, taking real values on real vector fields, I want to have a real coefficient for the metric. So in a non-commutative case, the analog of being real value is being self-adjoint. Okay, so exactly why we have this self-adjoint condition. So example, so I give a few examples. Okay, so flat metric, so it's when Gij is delta Aj. Conformally flat metric, so that type of metrics that have been considered before by Kohn-Tretkov, Kohn-Moscovici, Tizadeh, Al-Rali, and others. So basically, you do a conformal deformation of the flat metric by playing by a positive invertible smooth element. We can also consider asymmetric metric. So basically, it means so you just do only a conformal deformation on a square. Okay, and also a diagonal metric considered by Kohn Tizadeh, where you do so you do different conformal deformation on different squares. Okay, right. So once we have a Riemannian metric, you can define a notion of Riemannian volume and Riemannian density. So Riemannian density is given by integral against square root of the determinant of G. Here we are so CC infinity of theta m is a non-commutative ring. So it's not clear what notion of determinant we could use, but here you can use the fact that it's closed under holomorphic functional calculus, and define the determinant as exponential of trace of the log. So when you take a square root, you insert factor on f(e). Okay. So Riemannian density. So if you integrate against, so in a commutative case, density give rise to a measure by integrating against them. Okay, and so if we do that, we're going to get is a weight. So I call a Riemannian weight of G, the weight phi G, which is 2 pi n tau of u nu G. So nu G, this is the square root of the G. Okay. So the reason why we put 2 pi n is because in fact tau is not exactly the integral of the integral. This is integral divided by 2 pi n. So we include 2 pi n here, so that so what's really an analog of the integral is 2 pi n tau. And the Riemannian volume respect to G, so it's defined by the value of phi G at 1. So this is integral of constant function 1 against nu G. So we can compute this in the, okay, so I wanted to give example, but it's not on the slides here. So in particular, when theta equals 0, what we find is that the volume, when theta equals 0 and G is a flat metric, what you recover is, what you get as volume is 2 pi n, which is the volume of the ordinary motor. So this is consistent. So the normalization is consistent with volume, it's consistent with getting back the volume of the ordinary motors. So you can define a curve to space. So that's really important as like as domain of for the Laplace-Beltrami operator. So there are some subtleties about the way you define the inner product. So the way you do is that so we define the inner product on L2 theta n, so without G, as tau of u v star. So here we insert the Riemannian density nu G. So the inner product of uv is tau of u v star nu G. So what you can recognize here is in fact the GNS construction for the not for c theta n, but for its opposite algebra. And so it means that the life multiplication does not extend to star representation, but we get one by, if you like, applying the square root of the modular operator. So we get star representation in L2, in the curve L2 space, by conjugating by square root of G. Okay. So here, throughout the talk, A naught is going to be the conjugation of A by square root of G. Okay. Again, nu G, this is the square root of the determinant. So there's reason for that is because
Raphael,
yes,
we have a question here from Jonathan. Can you read the chat message?
No,
or
I
you
cannot
want me
read
to
the chat.
read it for you? Or maybe Jonathan, you can just ask Raphael directly.
Okay, I can get the chat.
Sure. So question was just about the formula at the top of that page. You have the nu of G on the right, or I guess equivalently, you could put it on the left, but why on the side instead of in the middle, which would be more symmetric? Since things don't commute, they might not give the same answer.
Yeah, actually, yeah. So basically, this is why you have to use this notation here. So,
Okay.
but it's tau of v star nu G u. So this way, nu G is in the middle. No, the reason is because it is okay. The reason is so that when you find the Laplace-Beltrami operator, we get an actual differential operator. And in fact, the way you define the Laplace-Beltrami operator use differential so it involves the Durham differential, which maps to differential one form. And differential one form are defined as a dual of the module of vector field. Module of vector field is the left module, and so this dual is the right module. So in a sense, you have to think right when you do this construction. But I will go back to this when I define the Laplace-Beltrami operator.
Okay, thanks.
No problem. All right, so actually it's here. So all right, so if I Laplace, so given any Riemannian metric, so with inverse G inverse, so the notation for the entry of the V inverse is with superior indices, J. So it defines an operator from on CC infinity of theta n, which is given by this formula. So the formula is analogous to the formula for the ordinary Laplacian on a Riemannian manifold, at least in a local coordinate. So again, nu G, this is square root of the G. And the difference is that instead, so in the commutative case, what you get is inside the dxi, you have a square root of the G, Gij. Here we are in a non-commutative setting. So instead of having a square root of Gij, we have nu G 1/2, which is fourth root of the G, Gij. And square root. Okay, so it's square root of nu G. So here it's not a quarter, it's a half. And so the way you get to this formula is actually because it's defined as d star d, where d is analog of the Theorem differential. So maybe if I explain, I'll explain the definition of the Theorem differential in the end of the talk. But the point is that, okay, so I just want to stress that it's really analog of the Theorem of the Laplace-Beltrami operator. And so I mentioned, so I give examples. So from flat metric Gij equals delta Ij, what you recover is the ordinary Laplacian with a minus sign. And when I conformally flat metric, so you can compute explicitly the Laplace-Beltrami operator. And what you get is you have a leading term, which is k to minus 2 delta u, minus this first order term. And first order term, because here you have k to the minus 1, k to the n minus 2, sorry. When n equal 2, this is, you get 1. And so when you take the derivative of 1, you get 0. And so when n equal 2, you get a formula, simple formula, delta G equals k to the minus 2 delta. It's reminiscent to the conformal invariance of the Laplace-Beltrami operator on Riemann surfaces. So key property of the Laplace-Beltrami operator is that's an so the elliptic differential operator. So elliptic means that the principal is invertible. And so key property is that one is a differential operator and its kernel is equal to C. And the reason why you get these two properties is because of our choice of inner product. So if you use, if you make, for instance, in a work of, I think, in talk of Masoud last week, in his work with Ashgar Gorpampour, so you get two operators which play a role of Laplace-Beltrami operator. So there is d star d, but in their paper, d star d, this is not a differential operator because it involves right multiplication by an amount of C infinity of theta m instead of left multiplication. And so we can do a conjugation to get a differential operator. But when we do the conjugation by, correspond to conjugation by square root of G, we lose the properties that the kernel of the Laplace-Beltrami operator consists of constants. Okay. So you have to be so you need to be careful with the choice of inner product. Well, in addition, delta G one can show, because it's elliptic and you have some elliptic theory on infinity torus, delta G is essentially self-adjoint and positive. So positivity comes from the fact that this is actually d star d. And yeah, and therefore, spectrum is discrete and consists of non-negative eigenvalue with finite multiplicity. So in particular, I can arrange the spectrum as a non-decreasing sequence where each eigenvalue is repeated according to multiplicity. The first eigenvalue is 0 and then multiplicity 1 because the kernel is exactly C as dimension 1. And you have an orthonormal basis consisting of smooth elements. So that's a notation here. the autonomous basis. Okay, so I will briefly speak about pseudo-differential operator. So exponential operators are seated with some class of symbol. So the symbol are smooth function on Rn with value in smooth noncommutative torus that emit an asymptotic expansion of homogeneous symbols, so satisfying this property. And the quantification is given. So you can it's not. All right. So each symbol gives rise to an operator by this formula. So here, so this is the integral here is actually an oscillating integral. Okay. And alpha minus s u is actually the action on of Rn defined by the so actually the one parameter will be defined by the canonical derivation. So in particular, alpha s of uj is just sj uj. So here psi and s are range over Rn, and again this is an oscillating integral. Point is that this is a generalization of differential operator. Namely, so if you have a differential operator, sum of a alpha d alpha, so d alpha is a multi-index. Then P is in form P rho, where rho size, this is symbol rho size is obtained by substituting I psi for del. So you have a class, so pseudo-differential operator have all the property of the standard classical pseudo-differential operator. So in particular, we form an algebra. And we have a noncommutative residue. Okay, so a noncommutative residue of an integral order pseudo-differential operator is basically the integral of the Cp, where Cp is the integral over the sphere of the symbol of degree minus n. Okay. So we can show this is a trace, and in fact, this is a unique trace on integral order pseudo-differential operator. So this extends, previous result of Fatizadeh Wong, Fatizadeh Ralrali. So Fatizadeh Wong and Fatizadeh Ralrali, they work in dimension 2 and dimension 4 respectively. And they prove noncommutative residue is a unique trace that vanishes on operator of sufficiently low order. So that is a unique trace. So this was extended by Levy, Nera, Pesha, who prove that it's a unique trace that vanishes on smoothing operators, it's a unique trace on symbol. But in fact, you have a true analog of the result of Zeki, noncommutative residue is a unique trace on the full algebra of integral order pseudo-differential operator. Okay, so it's an analog of the result of Zeki for classical pseudo-differential operator on compact manifold. So you can also interpret the noncommutative residue in terms of residue of zeta function. So I want to mention that, so all the results. So if you have an elliptic psi dO, and take another psi dO, you can form a function q to, you can look at trace of q p to minus s. So this will be trace class when a part of s is large enough. And in fact, I can show it as a homomorphic extension to all C with at worst simple poles. And poles are given by this formula, so they are given by a noncommutative residue. And important fact to stress is that they are actually when q is equal to 1. So you look at the function of p, so trace of p to minus s, so it has a homomorphic extension to C, and but there is no pole at s equals 0. So this more on the technical side can show that P is only elliptic. So it means that the spectrum of the principal symbol is contained in the positive half space. In this case, it can show that the function gamma s trace of to P minus s have rapid decay along vertical stripe, and this allows us to get each kernel asymptotic for trace of q to q of e to the minus tp. Okay, but I'm not going to need this for the stock. So we can now state the first main result of this talk. So this first version of Gauss-Bonnet theorem So consider a Riemannian metric. So this is to apply the results of the previous slide to the Laplace-Beltrami operator. You find that the zeta function of the Laplace-Beltrami operator has a homomorphic continuation to C, with at worst simple pole on half integers that are smaller than or equal to n/2, and there is no pole at s equals 0. I think we can give a slightly more precise result for the pole. Anyway, what you need is for talk is just pole at n/2 and the fact that there is no pole at s equals 0. So there is a version of the Gauss-Bonnet theorem of Cohen-Tretkov for noncommutative Tori in the case of conformally flat metric. So dimension n equal 2, we show that for conformally flat metric. Okay. So it shows that if you make a conformal deformation of the flat metric, we don't modify the value at 0 of the zeta function. That is, the value at 0 of the zeta function does not depend on k, and so that is, it's a conformal invariant. And if I can prove a much more general result, so namely, so the value at 0 of the zeta function is independent of G for any Riemannian metric and in any dimension. So the fact is true for it's independent of the Riemannian metric when G can be any Riemannian metric. Infer that it is topological invariant. Okay. So I will also explain why this implies a true version of the Gauss-Bonnet theorem in a few slides. So before getting to that, I'd like to speak about Weyl and local Weyl for curve noncommutative torus. So Weyl essentially, when you look at the Weyl, it will show that the eigenvalue of the Laplace-Beltrami operator grows like, I think it's n/2, times the coefficient, which is given by the volume. So here, what's going, you don't get the, so I define the volume in terms of the square root of the, in terms of tau of, so back here. Yeah, so volume is defined in terms of integral of tau nu g. So in fact, what you're going to see is that we don't exactly get nu g, but you get another Riemannian density, which is called spectral Riemannian density. Okay. Which is given by, so the integral over the sphere. So take a normalized measure by dividing by the volume of the sphere. And nu g is basically the norm of psi with respect to g. So it's square root of sum of g I j, psi I, psi j. Okay, so in fact, okay, so you can show that, well, actually, utila g is a positive anti-amount of C infinity of n. And when the metric is self-compatible, so by this I mean that the entries of G pairwise commute with each other. In this case, nu G agree with nu G agree with G that is square root of the determinant of G. Okay. So for instance, the functional metric of Borg-Pampour-Rallis that were a topic of Masul talk last week are instances of self-compatible metric. And by the way, when the entry is a pairwise commute, you're actually in a non-commutative ring. And in fact, you get the usual formula for the determinant of G in terms of the Leibniz formula, in terms of sum of alternate product. Okay, so Weyl law, can instead know the Weyl law. So Weyl law is okay. So here I give a value about terms of counting function. So lambda L of nu g are the eigenvalues of delta g, which is arranged as a non-decreasing sequence. So each eigenvalue is contained with multiplicity. So counting function says that, okay, so Weyl states that it's going to grow like lambda to the n over 2 with a coefficient Cn. So Cn here will be 1 over n times the volume of the sphere. So Cn times tau of nu tilde g. So nu tilde g, this is a spectral Riemannian density. And one metric G is self-compatible, that is the eccentric pairwise commute. Nu tilde G agrees with nu G, and so here you get tau of nu G, which is the volume of T theta n up to a normalization. And you also have a local version. So here I consider the sum of inner product with the eigenvector. So here is eigenvector of delta G with respect to the eigenvalue lambda L of delta G. Okay, so we take inner product of A, EL, EL. So A is a element of smooth element. Okay, and A naught, this is again, this is a conjugation of A by square root of G. So in particular, when A is equal to 1, this guy is exactly the counting function. So we can see this as a local version. In this case, what you get as asymptotic is, so it goes like lambda to the n over 2, and coefficient is Cn tau of A in tilde G. So basically, from this, you recover the weight associated with nu tilde G. So on Riemannian geometry, the local Weyl is related to quantum identity by Schnirelmann, Cohen-Verdier, and Zeldish. So it says that when you have a closed Riemannian manifold, and when the geodesic flow is ergodic, then you can find a density 1 such sequence, LK, such that, in fact, for all smooth function, inner product of f ELK, so that is integral of fx against non-square of ELKx, converges to the Riemannian measure divided by the volume of A. So QE is one of the main impetus for the quantum unique identity of conjecture of Winitz-Sarnak, which is related to the Riemann hypothesis, and basically says that you can actually have convergence when the manifold is hyperbolic. Okay, well, sorry, before. Okay. So it was shown by for arithmetic surfaces by Lindenstrauss. And question you can ask: is there a version of quantum complexity for noncommutative torus? So I don't know if this is possible, but that should be worth investigating. Okay, so next I would like to mention analog of contrast theorem for noncommutative torus. So we work in a setup of the quantized calculus of Cohn, which gives maybe I will briefly in variable correspond to operator in their space, real variable correspond to self-operator, variable which, bon, I mean, okay, connection is unstable. So analog of infinitesimal variable is like compact operator, and infinitesimal of order alpha is a compact operator whose singular value grows like k to the minus alpha. So here's a k plus 1 singular, the singular value basically the eigenvalue of absolute value of t, which is defined as square root of t star t. And important achievement of the quantized calculus is to have a notion of noncommutative integral, which is given by Dixmier Traces. So this is defined, noncommutative integral is defined on operator of infinitesimal of order 1, which are also called weak trace class operators. Okay, so you define this way, you get, so it's not exactly a binary, so the N1 infinity, you define this way, it's, okay, so it's a two-sided ideal. It's also interesting, it is also equipped with a quasi-norm. But again, this is not a norm, it's a quasi-norm, and so what you get is a quasi-binary ideal. So quasi, because it's not additive, you only have this inequality, it's quasi-subadditive. So quasi-Banach spaces are like Banach spaces, except that they are not locally convex. Okay, so all right, and okay, so you get okay, so the integral here is played by the Dixmier trace. So maybe I should mention this. Basically, maybe I gave a simple definition of the Dixmier trace. So start with an extended limit, and by extended limit, you mean a positive linear form on N infinity that extends the limit. That is, vanishes on sequences converging to 0, and it takes value 1 on the constant function 1. Okay, and given an extended limit, you can form, you can define functional on positive weak trace class operator. So we form the partial sum. So C minus T is the sum of the mu j T for j less than n. If mu, okay, what it means to be weak trace class, it means that mu j of T is a big O of 1 over j. And so when you take a sum of n first of them, there will be a big O of log n. So if you divide by log n, you get a bounded sequence, okay? And you apply the extended limit on this bounded sequence. And the result is that you get functional is additive on is additive, and it extends to a positive trace. Of course, you have many choices of extended limits, so this you get many Dixmier traces. In fact, the proof that this is additive is actually fairly simple, but it follows from these inequalities. So the first inequality is well known. It goes back to Anne. And even you have this also is inequality, which was found from so okay, mu j is j plus 1. Well, mu j is harmonic sequences when Dixmier trace 1. And they are, okay. And it can also show that there are many other positive traces. So you can introduce notion of strong measurability, saying that the operator is strongly measurable when all positive normalized traces agree in T. And contrast theorem, so that's for an example, as for a compact manifold. So, so consider a compact manifold prove that just for every positive normalized trace on the mixed class. So this goes back to Kelton, Lord, Potapov, Chef. We have an analog of the for physics. So every consider a non-commutative torus, and every absolute functional its non-commutative integral Dixmier trace is 1 over n its non-commutative residue. Okay, connection is unstable. So this improve earlier result of Fatizadeh, sorry, I misspelled Fatizadeh. Fatizadeh we prove only measurability in dimension 2 and 4, I think. And one consequence of this formula is that Dixmier non-commutative integral is defined only for weak trace class operator. So in particular, can go beyond, a priori cannot go beyond pseudo of order minus n. I cannot consider, it's not defined for pseudo of order greater than minus n. Okay, so non-commutative residue is defined for all pseudo-functional operator of integer order. So you can use actually the right-hand side as definition of the non-commutative integral for arbitrary pseudo of integer order. Okay. So there's another application of contrast theorem, which is Cohen integration formula. So when you specialize the contrast theorem for operator of the form f delta g to the minus n over 2, in this case, you can compute explicitly the non-commutative residue, and what you get is integral of f against the Riemannian density. So basically, what you see is that you get from Dixmier trace, so integral, recovers Riemannian measure. Okay. So this is true for so when f is smooth, it's direct application of contrast theorem, but you can extend the result to all f in L2. So it's not it's kind of significant result because multiplication by function in L2 are not bounded on L2. Okay. So there's you need first to show that even so multiplication by if you take an arbitrary function L2, so this is implication is unbounded. But when you compose with delta G to minus 2, you first need to show that this is actually a bounded operator. Operator is even weak trace class. Okay. Yeah, so you cannot go beyond L2. In particular, you can show the formula does not hold in general for L1 function. And then an analog of this result for a noncommutative torus. So it's proved in 2 steps. So okay, so I prove it first for a continuous version, and then this will be extended to L2. Get L2 version and collaboration with Edward McDonald, former student of Sukhoshev in UNSW. So clear Riemannian metric on the noncommutative torus for every A in L2. So operator A naught delta G is minus n over 2. So again, A naught, this is a compression of A with a new G, square root of that G. So this operator is strongly measurable, and its noncommutative integral is Cn times tau of A nu to G. So Cn again is 1 over n times the volume of the sphere. Okay. So this extend result of Laidonal, Janin in the flat case, and for function C theta n. And why you can so I prove it case where A is in C theta n, so in GNP. And you can, and why you can extend to A in L2 is because you have this analog of Spectral estimate, which basically say that if A in L2, operator A not delta G to minus n over 2 is weak trace class, and you can bound is 1 infinity norm by the L2 norm of A. So basically, to get the result in L2, you get from the result for C theta n by you extend from the A from the continuous case to the L2 case by some continuity. Okay, so okay, so now I would like to speak about the scalar curvature. So motivation for definition comes from the book of Kohn and Marcoli, where we define of scalar curvature functional for a spectral triple. So consider a spectral triple which is n summable. In fact, you need to assume maybe it has a finite dimension spectrum. So n summable means that so n summability is an analog of is meaning that you have a dimension n. So n summable means that the eigenvalue of the inverse goes like k to the minus 1 over n. And in this case, we find the scalar curvature functional. So the script A is minus 1 over C prime n, non-commutative integral of A absolute value of D to minus n over 2. So yes, not exactly the non-commutative integral. This is the extension by a residual trace. And C prime m is some positive normalization constant, which is chosen so that it recovers the usual notion of usual scalar curvature in the case of Riemannian spectral triple. So spectral triple associated to square root of the determinant. Okay, so if you apply this definition to this spectral triple associated by the square root of the determinant, you recover the integral against the scalar curvature. Actually, I forgot the f here. So here it should be a f. Well, you see f. Well, anyway, okay. Well, sorry. Right. Okay. Well, anyway, so it should be a f here. I'm apologize about that. So can define an analogous notion of scalar curvature for noncommutative torus. So define scalar curvature functional RG. So define on C infinity of theta n, and what you get is RG of A is minus 1 over Cn prime, non-commutative integral of a naught delta g through minus n minus 2 over 2. Okay. Again, a naught, this is compression of a by square root of determinant. And the scalar curvature is basically the density of that function. That is, you can show that this unique element of infinity of theta n, so noted kappa g, so that rg of a is 2 pi n tau of a kappa g. So it was essentially done in dimension 2, dimension 4 for conformally flat metric by Cohn, Moscovici, and Fatizadeh Rani. And so we call kappa g the scalar curvature of g. So I can give a formula in terms of symbol of resolvent. So the way this kappa g is set up, what you need to consider is not exactly a resolvent for delta g, but a resolvent for the so hat delta g, which is the compression of conjugation of delta g by square root of g. So I get integral over that involve the symbol of degree minus 4 of the resolvent. So the formula is fairly analogous to the previous formula for the scalar curvature, except here integration domain are compact, bounded. So it simplifies. So I believe it simplifies somewhat matters. I think you can in fact find a definition that's going to involve only delta g and not at delta g. In this case, the computation of the symbol is a bit simpler. Anyway, I'm not going to worry about computation of kappa g. In fact, this it can. So there is some preprint of Yang Liu, and essentially from his work, you can compute the scalar curvature in terms of hypergeometric function for a vast class of Riemannian metric. So essentially, probably even all self-compatible Riemannian metric, that is Riemannian metric whose entries commute with each other. Okay, so using this notion of scalar curvature, I can restate the Gauss-Bonnet theorem mentioned in the previous slide. So, okay, so the module of vector field is free, okay, and so their characteristic must be 0. And okay, so then you can reformat the Gauss-Bonnet theorem I mentioned before in dimension 2 as follows: for any Riemannian metric on G, the integral of the scalar curvature against yeah, so that's why again the square root determinant is 0. And 0, but 0 is also the layer characteristic. So you get equality between the integral of the scalar curvature and the layer characteristic. So it's true analog of the Gauss-Bonnet theorem. So this was deduced from hard and Nafli computation. Also, I think now is a bit simplified by the work of Yang. In case of conformally flat metric, so Trikov, Fatizadeh, Rani, and also in case of asymmetric metric, Dabrowski, Stars, and Dorfman. Okay. All right, so it's 10 minutes left plus epsilon. I can speak about index theory. So basically, it's a project in work in progress, and this is going to get essentially. So there's also work by Matai and Jonathan Rosenberg. So essentially, what I give is like a cyclic cohomology version of Matai Rosenberg work, and we also work by Fatizadeh, Luef, and Tao. However, they didn't compute explicitly the Cohen-Chern character. All right. So I just want to recall the local, the Cohen-Chern character for spectral triple. So spectral triple is an analog of Riemannian manifold, analog of vector bundle given by projective modules. What's the role of the RAM cohomology and the RAM homology is cyclic cohomology and cyclic cohomology of Cohen and Sagan. And an important application of cyclic cohomology is the construction of the Cohen-Chern character that compute the index by pairing the condition character, which is in a cyclic cohomology class, with a cyclic homology condition character. So basically, in the same way as you can define, you can take indices of twisted Dirac operator. When you have a Dirac spectral triple and a module U, you can define a twisted operator, D nabla E. So basically, nabla E would be a connection on E, stable connection. And this find an index problem. So your index depends only on the case theory of E. Okay? And it's computed, if you like, by pairing the case theory with the condition character. Okay, so then the question of giving a formula for the condition character. So there's a formula with the GLO cocycle and the Cohen-Muscovich cocycles and result one cocycles. Here we're going to use only the Cohen-Muscovich cocycle and also the original definition of condition character by Cohen. I don't know if I need to recall the definition of spectral triple, but the spectral triple consists of an algebra A, which is represented in a Hilbert space H, and anti-commute with self-adjoint unbounded operator. So we are going to suppose it's even. So in fact, there is a Z2 grading. So A is even with respect to the Z2 grading, while D is odd. Essentially, A and correspond to the topology, while D correspond to the metric data. So a prototype of a spectral triple is the Dirac spectral triple, so given by the Dirac operator. Okay. Cyclic cohomology. Okay. So still with a unitary algebra. So a periodic cyclic cohomology is given by this quotient complex. So the chains are given by, so quotients are multilinear maps on linear form on A. Okay, so group them according to parity. And then you have two operators. So a little bit is Hochschild boundary operator, so that's degree 1, and capital B is Kohn-Reinhardt operator, which has degree -1. In case of example, 1A is a smooth function, algebra smooth function, and the periodic cyclic homology recovers the Durham homology. And in this case, the operator little p is actually 0, and the operator capital B is a Durham differential. Okay, so so we're going to construct a spectral triple on noncommutative torus. Construction is analogous to the construction of Cohen-Tretkov, and also in the flat case construction of Cohen in his book. Except I like to make it a bit more intrinsic. So find a Rank module of, or I say more abstract. The Rank module of differential one form. Okay, so you have a module of vector fields, so the left module. So you define a module of differential form as a dual module, and what you get is a Rank module. So from the canonical derivation, you get basic one form. So theta 1 dot through theta n. This condition. So theta I dj is delta ij. And you can define the Durham differential. So in fact, this will be the dual version of the gradient. So differential of u, this is sum of theta j dj. Again, the fact that x theta is a left module implies that omega 1 theta is a right module. On the other hand, since it's a free module, you can also define a left module structure on omega 1 theta n. So in fact, you have a bimodule, except that the left module structure will depend on the choice of this, while the right module structure is somewhat interesting. Anyway, okay. So suppose that. So again, this is in progress. So I just look at the case, simplest case for n equal 2. So define a complex structure on theta. Okay, so n equal 2, you don't have two derivations, d1 and d2. So you define a complex structure as a splitting of x theta in terms of holomorphic vector field and anti-holomorphic vector field. So holomorphic vector field is spanned by d1 minus I d2. at the level of forms give a splitting between 1,0 form and 0,1 form, and the differential split as del plus del bar, where del bar maps to 0,1 form. Okay, and can show that the splitting is orthogonal respect to a given Riemannian metric, if and if this Riemannian metric is locally is conformally flat. Okay, so we're back in a setup of Cohen and Trekov. All right, so suppose that n equal 2 and Gij is a conformally flat metric. Then you get twisted spectral. Okay, so we can get a spectral triple. So it's not exactly a spectral triple, it's a twisted spectral triple. So naming that you don't have the condition of commutator, you get bounded commutator if we twist the commutator. Anyway, you can assume it's a spectral triple for now. In fact, for spectral triple, twisted spectral triple, we also have a notion of Conchian character. And so the operator, the Dirac operator is d bar plus d bar star, and it acts on, so there's the curve L2 space, L2G T theta 2, so I defined previously. And you can define a Hermitian metric on one form and complete with Hermitian metric and the Riemannian metric to get Hilbert space, which is denoted by omega G 01 T square theta. Okay. And so the last result. So we have a Conchian character, and we like to compute it. Okay, and then you can compute it, and it's represented by the quotient cocycle tau2 of God, which is given by this. Okay, and the way you proceed is basically, so result is maybe 90% or 95% of results are already in the literature, in particular the work of Cohen and Cohen-Moscovci. Okay, the only new thing is to observe that the Conchian character. So here, a spectral triple assisted with a conformal deformation of the flat metric. The only new observation is that this doesn't, Conchian character does not depend on the conformal factor, conformal deformation. So it's analogous to, work with Hang Wang, look at index formula and conformal geometry. And so we constructed some spectral triple assisted with conformal diffeomorphism. And we showed that that the Conchian character was an invariant of the conformal class. Okay. And similar argument, an elaboration of this argument can show that the Conchian character does not depend on the conformal factor. Okay. So you can assume that k is equal to 1, and when k is equal to 1, you cover the, so you have an ordinary spectral triple. Okay. And in fact, the Conchian character is represented by the Cohen-Moscovci cocycle. And the Cohen-Moscovci cocycle was, even so, is not explicitly stated, is actually computed by Cohen and Moscovci in their journal of the MS. So you can apply their formula, and what you find is that basically the Cohen-Moscovci cocycle is in dimension 2, so we have two components. So the component degree 0 is 0, and the component of degree 2 is exactly the quotient tau2 of Cohen. In particular, so this allows us to compute index problem by pairing tau2 with Conchian character, the Conchian character in cyclic homology. All right, so that's it. Thank you very much for your attention.
Thank you very much. Do you have any questions or remarks?
Okay.
If there's no questions, let's thank Raphael again for a nice talk.
Thank you.